Hey, it's Random Code here, and today we're going to continue with FNF code, and we are now at day 10. And day 10 has a longer introduction, because today we're kind of looking at some kind of two-dimensional map, where we have some kind of route, where in part 1 we kind of have to find this route from a starting position, and then find what is the furthest point we could walk following this route. And this route is then constructed by ASCII characters. We have some pipes, dashes, and some letters to then define different boundaries. Example L is going to be the left bottom corner, and we see down here an example of a circle. So we have the pipes at the side, the dashes on the top. 7 is going to be the right corner, the top, F the left, L the left at the bottom, and J the right bottom corner. And we will then have a task where we are given an S. First I would find S. And from S, we then need to expand using some kind of search. And in my case, not an exactly depth first search implementation, but it's gonna simulate it more or less. Because we only have one path, and I'm kinda not visiting already visited nodes, so yeah, but that's the approach. And at the end, we end up having some kind of relatively complex setups. We need to find all the paths. And here's then an example. From SR starting position, we can then see we move 1 to each side, and 2 to 3 and to 4. So the furthest point we could walk in this setup would be 4. And to then solve this problem, I'm following a few basic steps. So I would first find my S, so my starting position, from my inputted pipe maze, which is what I will call it in this video, which is more or less just a list of characters. So each line is going to be its own list. And we would then, from S, simply find the next positions. And this is then more or less just going to be replicated until we hit the end condition. So in general, I have this find farthest away, where we first, so again, the first two positions after S, it could have been S as well. I then find my first path to the right and to the left. So as we saw in this example, I have my starting position. I'm then kind of searching in both directions simultaneously, which will then allow me to simply have a while loop saying, while the first path and the second path are not the same node, then keep going, and we then simply have a counter. So we just simply go one by one step at a time in each direction. At some point, we're going to meet. Our first and second node is going to be the same node, and we stop, and then we simply have the result from a counter. So pretty simple. And of course, this looks very, very simple, but we have this kind of position object in Java where I'm handling a lot of this logic behind the scenes. For example, we know based on our current node in which direction are we moving, because they only have valid directions. You cannot walk in all directions if you're coming from this direction, and you know where the next direction is going to be, and so on and so on. There's quite a lot of code here. I'm not going to go through all of it, but also kind of important. I've implemented equals and the hash code allowing me to compare these position objects, and it's simply been defined that objects are the same if they have the same x and y coordinates. But that is a relatively quick walkthrough of the concept of part 1. You just have a starting position, then kind of search outwards from the starting position until I hit the same node from each direction, and then I counted my path. What is then created in kind of part 1 is that we end up having some kind of border around some shape, and in part 2, which is a bit more complicated, we then need to find all the tiles inside the border and count how many tiles are inside the border. And what might become kind of obvious is that these patterns are kind of complicated. For example, here we have a pattern where it's going in and out. So we have a bunch of nodes that kind of looks like they're inside the pattern, but they're actually not, because they have a way out. And in this case, the way out is 1 tile, but it could also be 0 tiles. Meaning there are quite a few things we need to account for, like quite a few ways to do it. And I tried to do some kind of smart way at first, but I couldn't get it working. So after a bit of research, we're going to be using the even-odd rule, which then simply allows us to, from any position, simply check, we're going, for example, in this case, I'm just going to go straight to the right. How many borders am I crossing? And then depending on the border crossed, I can then kind of know whether or not I'm inside or outside, or I started inside or outside the figure, which then simply allow us, depending on the amount of borders crossed, to know if we're inside or outside of the figure. But Then again, because in our case we have these corners, it makes it a bit more complicated. But then using some of the functionality from part 1, I just simply find all the edges at first. I will then simply just go through every tile. This is not optimized at all, but just going through every tile in my input data. And then simply check in when I'm from this tile, is going to the right, how many borders am I crossing, and then depending on the borders crossed, I can then know if I'm inside or outside the figure from the starting position. And there's quite a bit of code, but the general concept is that we have this simply is tile inside checker from any given XY position. And I would then first kind of extract the slice, so all the nodes to the right. Then from all the nodes to the right, I just simply go through each of them, extract the specific character on those positions. I then do a bit of cleaning, meaning we only keep the letters in this slice, which are a part of the edge of the figure. Because that's the only thing that's kind of interesting. We need to know if we're inside or outside of this figure, so we're removing any extra data. I then was a bit lazy, so I'm just hard coding that S is in my case the same as a 7. But otherwise, we create some kind of method that would find the S for this given solution or the specific input. I then need to find the amount of crossovers, and if we're crossing a pipe, it's just simply going to add by 1. I then remove all the pipes after adding all the crossover counts by the pipe, and we then need to take into account how we're crossing our corners, and if we're crossing corners, which then going from like up to down, so it's going to be a straight line, it's going to count off 1. But if we're crossing and then going from down, then straight down again, it's going to be 2 lines, which more is just all of this. It's a bit complicated, but I hope the general concept makes sense. And then in the end, we then simply defines that is within simply our crossover count modulus 2 not equal to 0. Simply meaning if the crossover count is odd, we started within the figure. If it's even, we did not. And just to showcase again in these examples, if we think of here, for example, we cross 2 corners, so it's going to be even, and we're not inside the figure, where here, for example, we cross a single edge, so we are inside the figure. And that is very much my solution. I'm not going to go through it line by line. There's quite a bit of code, and this is very much not optimized. And what's also very clear, when I run it, it takes about 5 seconds, because we, for each letter in this quite large file, need to check all the values to the right of it to find if it's inside or outside the figure from this position. We simply add them together, and in my case, I get that I have 443 tiles inside my figure. But that is very much what I wanted to showcase today from day 10 of Advent of Code. If you enjoyed this quick showcase, please leave a like and subscribe, and I wish you all a wonderful